Hey everybody, today we're doing an example of finding volume using the shell method. Here's the problem we're going to do. Triangle with these three vertices is rotated about the y-axis. Find the volume of the solid enclosed. So let's start by drawing the region. There it is. I plotted the 3 points and connected the dots. I've chosen to draw a vertical rectangle. It is possible to do this problem by drawing horizontal rectangles and using the washer method. That involves writing 2 integrals, not just one, and that's why I'm choosing not to do it that way. Next, let's actually try and draw the shape that's going to be generated, both when the rectangle rotates around the y-axis and when the entire triangle rotates around the y-axis. So the sketch there on the left gets a little busy, c'est la vie. It's sort of a donut shape with some sharp edges on the inside, the top, and the bottom. The general volume formula for the volume of a single shell is dV equals 2 pi times the radius times the height times the thickness, dx. The radius of the shell at x is just x, the distance from that vertical rectangle to the axis of rotation. The height of the shell is going to be the height of the rectangle, so it's going to be sort of top curve minus bottom curve. And because we're given the points where that are defining these triangles, we know where the rectangles are going to begin and end. They're going to begin at x equals 1 and end at x equals 3. So the limits of integration are not a problem in this particular example. Okay, so let's actually find the height of this rectangle. We want to do top curve minus bottom curve, so we're going to need the formulas for the top and bottom curves. These are lines, so let's find the slope of each one. The slopes are 1/2 and -1/2. And both of the lines pass through the point 1, 3. So we can use point slope form to get those equations. I've done a little bit of simplification to get the equations -1/2x plus 7/2 and 1/2x plus 5/2. The height of the rectangle is going to be top curve minus bottom curve. So here's what I get. I do a little bit of simplification and I get x minus 1. The way I interpret that is that if you give me an x value between 1 and 3, I'll plug it into this formula and get the height of the rectangle at that x value. That's easy to confirm, for example, at x equals 1, where the rectangles have no height, 1 minus 1 is 0, and at x equals 3, where the height of the rectangle is 2, 3 minus 1 equals 2. Now let's start plugging things into our general volume formula, 2 pi integral from a to b, radius times height dx. So 2 pi integral from 1 to 3. The rectangles are going to start at x equals 1 and end at 3. The radius of the rectangle at x is going to be x, and the height that we just determined is x minus 1. Now we just have to anti-differentiate this. So I'll simplify the x times x minus 1, anti-differentiate, plug in the limits of integration, do a little bit of arithmetic, and overall I get 28 thirds pi, about 29.32.